we flip the paradigm. Instead of moving the data across all of these locations into one place to train it, we push the compute to where the source of the data is, and we train local models on each of these data silos, and only move the model weights to combine them.
Chong Shen is a research engineer at Flower Labs who created a leading open source framework for federated learning, a pretty established technique to address the training and privacy and data ownership challenges in AI. Every foundation model you've ever used, from Claude to GPT to Gemini, they were all trained the same way. Scrape everything into one place and process it there. The problem with this approach is that the most valuable data can't be scraped. Medical records, financial transactions, proprietary research. Without giving models access to this information, the models will never develop capabilities in these domains. So medical diagnostics will come from literature and academic research, which is good, but not as good as if it had been trained on the millions of patient records and actual diagnoses. Federated AI solves this by asking, what if the model came to the data instead of the other way around?
So at Flower Labs, we want to enable everyone to be able to collaboratively work on AI. So that means being able to build AI models together without revealing or sharing a lot of private information. Typically, what's been done to produce these kind of big AI models is to collect all data and put them into one single data silo or database, right? So there's terabytes or petabytes of data all in one place, more or less. And you would then train a very huge, large parameter model, right? But the problem with this is, in reality, all the data is not in the same place, right? For instance, there are some industries that have the data all in silos. So the most obvious ones that come to mind are in healthcare. There's a lot of personal and private data that cannot be shared across hospitals or sites and silos. Similarly, in finance, it's very, very difficult, almost impossible to share data across financial institutions and so on and so forth. So this is where the federated learning comes in. We flip the paradigm. Instead of moving the data across all of these locations into one place to train it, we push the compute to where the source of the data is, and we train local models on each of these data silos, and only move the model weights to combine them.
Frontier models have typically required two raw ingredients to train: data and compute. Clearly, we're watching compute scale as more data centers are built out. But data, well, that's being scraped. And this is why what Flower does is so important. Its approach unlocks a new data set, and in many instances, the most accurate set. Previously, if you wanted healthcare data, financial records, proprietary research, the cost wasn't dollars. It was permission to download that private data at a massive scale, and that was never going to happen, so it didn't. Federated learning changes that. Now models aren't asking for the data, they're asking for just access to train on it. The data never leaves the building, only the learned weights travel back.
So this solves a couple of problems. Firstly, you don't have to move the data from the data source. You're able to leverage all of the compute at the edge, close to where the data sits, and you'll be able to enable a lot of privacy enhancing technologies that can protect all this data from being misused or abused. When you pre-train them on more or less the public data, then you have a very good foundational model that understands English. It can produce a coherent, understandable sentence or paragraph. But once you want to refine them on this very specific domain knowledge, like in healthcare or finance, this is where you don't have the data, right? So it's very hard to gain access to this out data. This is where the federated AI concept comes into the picture. So what this means is you take one hospital A, you deploy a client. So in our terminology, in the Flower Labs terminology, it's called the supernode. So day zero, infrastructure stood up. Now we have a federation that is ready for doing this kind of workloads. Then day one, when someone wants to, when the team wants to train the next level of the next generation of foundation models based on this medical data, you could take a base model, let's say a permissive licensed base model, language model that's open sourced, for example, and you say, okay, I want to now fine tune it so that it learns on this the information from this healthcare application. You don't have to train the full model. You don't have to fine tune the whole model, right? Because it might be like hundreds of millions of parameters. If you do that, it can actually be worse. If you try to take all the model weights, and try and fine tune it on all this specialized data.
What is exciting about this approach is that it's relevant not just to the hyperscalers like Google or Anthropic, but to the domain companies who own that data. They can take an off-the-shelf open model and fine-tune it on site, adjusting a small subset of its weights on domain-specific data. The base model already knows English, it already knows logic. You're just teaching it the language of your industry, a hospital's CT scan archive or a bank's transaction patterns. The model learns locally, so only the updated weights travel back. There is a lot of opportunity here.
Once this smaller subset or smaller group of weights are trained, you move these weights back to the superlink, to the aggregator side, and you combine them. Let's just say the simplest way would be like averaging the weights. You then produce an updated global model that should, in principle, be better than the base model that you started off with, and then you evaluate that against a predetermined set of criteria that these domain experts would know, and then you monitor it over a couple of rounds. But let's just say the detections of tumors in CT scans. And what you want is to be able to have a model that is able to have very good metrics there, very good accuracies. So the predictions there would be the ones that could be assistive to all these the medical practitioners, right? So given this scan, they could firstly have an expert evaluate that, get a certain degree of to have the first pass of what the diagnosis would be, and then when you run through this type of computer vision models, these foundation models, it could give its prediction, and it could also give the confidence of this prediction. And I've read as well in the past, there were a couple of these AI models that were able to pick up this type of edge cases where it was very hard to identify, and they were able to assist the doctors to identify them. I think there's a huge opportunity for a lot of industries and companies, and it's something that we're speaking to a lot of users about. We've definitely seen a lot of interest in that space across many industries.